transferring heat to a wire will not generate electricity. The main idea is that you have to have a channel in order to perform the work. Transferring heat to the paddle wheel will not cause it to rotate. So let me show you what. So if you don't have a channel, you cannot produce a useful work output from there. You see, it says the second law may be used to identify the direction of processes, so quality as well as quantity. So it should be a one-way process. So bodies with relatively large thermal masses can be modeled as thermal energy reservoirs. A source supplies energy in the form of heat and sink absorbs it. This is the definition of source and sink. So you see this diagram I drew earlier. This diagram is for heat engine. The schematic diagram or the sketch for a heat engine. It is saying that the heat is traveling from hot to the cold body reservoir, and during that process we get the work output. That's the main idea. And the example is steam power plant. So here this is steam entering this is steam, okay, at this moment. Once it performs work output, and the same steam enters a condenser where there are some air cooled condensers or water cooled condensers, and the steam loses heat to the environment and converts into water, and the water pumps the water to high pressure to the boiler, and the boiler makes the steam. Heat is being supplied. We also call it as a Rankine cycle. So let me show you the next slide here. Okay, so this is the thermal efficiency of heat engine, which is which I explained you earlier, Q1 minus QL over QH. So if you take a look here, I'm sorry, did I make a mistake here? I make a mistake here. It's good that I should have written it upside down. So the desired output is the work output. I will correct it in the lecture recording. So I'm sorry, this is Q. So let me make sure this is correct. Please write down this formula. This is correct now. We call it as a heat engine or thermal efficiency. And for can we save Q out? Can we just not take the condenser out of the plant and save all of the waste energy? The answer is unfortunately from no. There must be some heat to be rejected in order to perform some work done, which is the second law. Second law states that you cannot perform uh, a work output until unless you lose heat to the environment. So that's what the second law. If you do not reject the heat to the environment, then this is impossible. This violates the Kelvin-Planck statement. So no heat engine can have a thermal efficiency 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So it is impossible for any device that operates on a cycle to receive heat from single reservoir and to produce a net work up. So you cannot have a complete 100% work output from the heat. You must have some heat to be rejected to the environment. Now we talk about the refrigeration cycle. So what happens that in the refrigerator cycles, the compressor compresses the freon or any other fluid, and condenser makes it liquid, and this further changes the temperature, and liquid evaporates here, and then this is liquid here, and this is gas here after the evaporator in the evaporator coils in the refrigerator. So let me show you the schematic for this one. So I want to make sure that I did this one correctly here. So coefficient performance here for a refrigerator cycle. And this is correct. So the only mistake was on the heat engine part, that I should have written in the numerator the work output, the net work divided by the heat supplied. This was a mistake. So in this case, this is schematic of the refrigeration cycle. So work is done by the compressor. Condenser releases heat to the environment, and throttling device reduces the temperature and becomes liquid, and liquid refrigerant becomes gaseous in the evaporator. Okay, so can the value of COP refrigeration is, can it be greater than 1? Yes, it can be greater than 1. The third device is the heat pump, where the desired output is the QH. So this is my QH. In the winter season, we run the same air conditioner to in the reverse cycle, where the coefficient performance of the heat pump becomes the desired output divided by the work input. And the work input is again QH minus QL. And if you just redo this, 1 minus QL over QH. And that is true, and this is always 1 plus COP of R. COP of heat pump is greater than COP of refrigerators plus 1. You can prove it. Look over here. If you do this, COP of refrigeration cycle is QL is the desired output, QH minus QL plus 1. So if you do the math here, QH minus QL, QL minus QH plus QL, sorry, minus QL, QL minus Q. I'm sorry, this is cancelled by this, so you're left with QH. So this is the coefficient of performance of heat pump, which is 1 plus the coefficient of performance of the refrigerator cycle. So don't worry about this slide. It's not that um, important. Okay. Now the Clausius statement. Clausius statement is for refrigeration cycles that the refrigerator cannot work until unless you spend some work. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from low temperature body to high temperature body. You have to spend some energy. So if this is zero, then it violates the Clausius second law. So you must spend some amount of uh, work or energy in order to let the heat flow from cold body reservoir to the hot body reservoir. Okay, let's do one problem. A heat is transferred to a heat engine. So if I draw the heat engine, so heat is transferred to a heat engine from a furnace at a rate of, so Q dot H, high temperature reservoir. This is Q dot H. So this is just a rough sketch to explain you. So heat is transferred from the furnace, which is a high temperature. So, and if the rate of waste heat rejection is to the nearby river, this is river, okay? So we have to reject some heat to the river. So Q dot L, so I would say Q dot H is 80 megawatts. Q dot L is 50 megawatts. Determine the net power output. So you have to find out the net power output, which is this formula. Sorry, this is 50. This is 30. And it is also asking the thermal efficiency of this heat engine. So thermal efficiency is the desired output, which is the power output, divided by the heat generated inside the furnace. So desired output is 30, heat is 80. I'm sorry, this is 30. Let me double check. This is 30 over 80. Yeah, this is 30, 37.5%. So let me redo this over here. Please take a look at this. So if I copy and paste this into our notes, if you have understood this problem, write down yes. If not, then you can ask your professor any question. That's good. Okay, let's do the next question here. Let us solve this problem. A car engine has a power output. So power output 55 horsepower. And we know that 1 horsepower, that is in BTU, I will say 2545 British thermal unit per hour. And the thermal efficiency is equal to 24%, equals to 0.24, equals to Q dot, I'm sorry, this is equals to W dot net, power output divided by Q dot H. Determine the fuel consumption rate. So if you understood, the question is, what is M dot F? Fuel supply. So M dot F, fuel being used, and that is equal to M dot F times the HV. HV, guys, this is known as heating value. Every fuel like gasoline has its heating value, like diesel has its own heating value, and the heating value for the gasoline or for this fuel is 19,000 BTUs per pound mass. So if you burn 1 pound mass, you generate 19,000 BTUs. So let's find out from this form. I'm gonna target this formula and find out what is my Q dot H. So can I write down Q dot H equals to W dot net divided by 0.24. So Q dot and W dot H is 65 into 2545.24. So that will give me, let me write down here in my calculator, 65 times 2545 divided by 0.24. 1 second. There is a little error here, so let me check. This is my, yeah, divided by. This is correct. So this is my Q dot H. So let me write down here Q dot H 689,271 BTU per hour. So we know that this is equal to M dot F times 19,000 BTU per pound mass. So you just have to do the math here. M dot F equals to 689,271 divided by 19,000. This is BTU per pound mass, and this is what it is. This is equal to BTU per hour. So you're left with pound mass per hour for this consumption, fuel consumption. So if I do the math here, 689,271 divided by 19,000. I got 36.28, you can assume. So this much is fuel is being consumed, this much pounds per hour. This is your answer. So let me zoom out a little bit to show you what I did over here. I used the thermal efficiency formula, and I did this conversion from horsepower. How to go from horsepower to BTU per hour? You need to understand this conversion. Do you understand this question? Okay, that's good. Do you want to have a mini break or early release at this moment? Okay, I will release you early. That's good. So let me start the next example here. Let's do the question in the book. So I'm gonna show you question in the book here. 16E. This chapter is very easy as compared to previous chapters. You just have to use a few formulae, not much. So let us solve this problem in our book. A heat engine has a heat input. So this is our heat input, Q dot H. You see 3 into 10 to the 4 BTU per hour. This is 4. And a thermal efficiency, 40%. Calculate the power it will produce in HP. So power, net output power equals to 0.4 BTU per hour. And we know that 1 horsepower. Let me change the color here. So can I go from here? So W dot net or power output. So this value so the answer is in horsepower. If you do the math, let's do this math together. 0.4 times 3 in 10 to the 4 divided by 2545. 2545. 4.71 horsepower. Do you agree with your professor? Will you be able to solve these problems in your quizzes or test? Okay, let's do another problem here. You see, this chapter is very easy, just very small formula. The main formula, thermal efficiency for heat engine. This is the main formula. Okay, let's find out the next answer for this problem number 17. Thermal efficiency of the heat engine. It is 40%. It produces this much power. What rate the heat transferred to this engine? So we have to find out the Q dot H in kilowatts. So remember, 1 horsepower, it is equal to 746 watts. So let's do this over here. And according to this formula, so what is our 30? So I'm gonna write down 30 horsepower Q dot H. And you just solve this math. So let's do this math together. So 30 times 746 divided by 0.4. About 55950 watts, correct? Or 55.95 kilowatts is the heat being supplied to the engine to perform that much work output, which is the horsepower. Let us solve another problem here. Let's skip this one. Yes, 21. Let's solve the question. Some of the problems which I'm solving are also the part of the homework, but it's okay. You are here to learn. You can reproduce. Okay. One second, I have to do the setting. Okay, let's do this question. A steam power plant with a power output of 150. So power output at a rate and consumes coal at a rate of, so mass flow rate of the fuel, it is 60 tons per hour. How do you go from 60 tons per hour to kilograms per second? So we know that 1 ton equals to 1000 kilograms. Then it is easy. 60 tons, 1 ton, 1000 kilograms. 1 hour, 1 hour divided by 3600 second. Hour cancel by hour, tons cancel by tons. So the scaling factor is, so let's write down over here 6, 1, 2, 3, 4 divided by 3600. I got 16.67 kilograms per second. That's that's a very high rate of consumption. 16 kilograms per second mass flow rate of fuel. And then it says if the heating value, so heating value of coal is given. So if you know the heating value, which is 30,000 kilojoules per kilogram, can you find out the Q dot H? Yes, you can. Look, mass flow rate times the heating value is the formula for that. 16.67 times 30,000. What is that? So let me do this. 30,000 times 16 point, about 500,000. So let's say 5 into 10 to the 5 for the sake of simplicity. This is in kilowatts, correct? How is it in kilowatts? Let me show you. Let me show you over here the mass flow rate of it, it is kilograms per second. Kilograms per second, and this one is kilojoules per kilogram. Kilogram cancelled by kilogram, you are left with kilojoules per second, which is kilowatts. And now once we know the heat supply to the engine or steam power, so not in this case, it's not engine here, determine the overall efficiency of the plant. So that's we can find out. We know this is the power generation, 150 megawatts. This is the heat supply. So let me write down the formula. Thermal efficiency equals to the power generation divided by the heat supply to the steam power plant. How much is it? 150 into 10 to the 3 kilowatts, 5 into 10 to the 5 kilowatts. This is, make sure this is in same units, either is megawatts or kilowatts, should be the same numerator and denominator. So what you're left with, so multiply by 100, correct? So I can write down here 150 divided by 5 times 100. 30%. So this steam power plant is 30% efficient. Do you guys understand this question? Let me know if you understood this problem. Okay, that's good. Let's do one more problem. An automobile engine consumes fuel at a rate of 22 liter. So the volume flow rate of fuel, this is not the mass flow rate, but this is liters per hour. 22 liters per hour. And we can find out the mass flow rate. You remember the density, mass per unit volume, or mass flow rate per unit. It doesn't matter if you divide by the time in the numerator and denominator. It doesn't matter at all. So V dot. So can I write down M dot? I'm interested in M dot here, which is equal to density times the volume flow rate. The density is for the fuel. It is 0.8. So I have to convert it into. So let me write down 0.8 grams per centimeter cubed. 1,000 grams equals to 1 kilogram. So let's do this conversion here. So 0.8 times 100 power 3 divided by 1,000. I got 800 kilograms per meter cubed. The density is and from here I can write down 800 times. You have to convert into meter cubes per second. So how would you convert volume flow rate in meter cubes per second? We know that 1,000 liters equal to 1 meter cubed. So we just do the math here. So can I write down like this? Okay, 1 hour. This is in hour, correct? It's not in second. This is in hour. So I have to convert hour into seconds by doing this conversion. 1 hour equals to 3,600 seconds. So let's do the calculations here. 22 divided by 36. 1, 2, 3, 4, 5. I got 6.11 into 10 to the negative 6 meter cubes per second. And once I get this, I can plug this in over here. Let me rewrite here. So now I can rewrite here and 6.11 in 10 to the negative 6 meter cube per second. And for this one is kilogram per meter cubed. For the density, meter cube cancels, we're left with kilogram per second. You got my point? So let's write it down here. The mass flow rate of fuel, this is our fuel, and then you can just do the math here. 800 times 6.11 raised to the power minus 6. Uh, 0.00489. This is in kilograms per second. And now we have found the mass flow rate of fuel. Now it is asking, it delivers this much power. So the power it delivers is W dot net. Fuel has a heating value. So the heating value is given. So you have to find out efficiency. So this is our question. Efficiency, which is equal to unknown, but it is equal to power output, net power output divided by the heat supply to the engine. Okay, now let's use the same formula. I'm going to use the same formula to find out the answer. So I'm interested in finding out the heating value. So Q dot H equals to M dot F times the heating value. In our problem, the data has been given 44,000 is the heating value. So 0.004888 times 40,000. And this is in kilograms per second. I would say kilograms per second. So you're left with kilowatts. So let me write down here kilowatts. So 0.004888 times 40,000. This is 90, 195.52 kilowatts. And our power output given in the question is 55 kilowatts. So can I write down like 55 in the numerator? 55 kilowatts in the numerator. Denominator 195.52 kilowatts in the denominator times 100. So can you do the math and help your professor? Oh, 1 second. Is it? Oh, I'm having different answer. I'm sorry. This is 44,000. This is not 40,000. There is a little error. This heating value is 44,000. So I have to change this number. It is not 44,000. It is not 40,000, but it is 44,000. So I got 215. So let me rewrite here. I got 215.07. So do you get 25.6%? That's good. Elsie says it matches. She seconds my answer. That's good. Okay, we have done the Kelvin statements problems. So I will start from here for refrigeration cycles next time. Thank you guys. I'll see you next time.